How can one planet help solve a mystery that has haunted science for more than 100 years? What if NASA's latest images of Jupiter are not just beautiful, but proof that something strange and powerful is happening there right now? And before we jump in, do one quick thing for me. If space stories that make you rethink the universe are your thing, tap like, subscribe, and share this with one friend who still thinks Jupiter is just a giant ball of gas. Most people look at Jupiter and see color. They see bands, storms, and that famous giant red eye staring back from space. They see a planet that looks dramatic but familiar. A giant world we have photographed for years. A world that feels huge, distant, and strangely well known. But what if that picture is wrong? What if Jupiter is not just something to look at? What if it is a live laboratory where nature is showing us, in real time, how some of the most violent events in the universe actually work? That is why this story matters. Because NASA's Juno mission did not just send back another nice image. It sent back evidence. Evidence that particles near Jupiter were being pushed to incredible speeds. Evidence that a process scientists have argued about for generations may really be happening. And evidence that Jupiter is even stranger, more complicated, and more important than we thought. To understand why this discovery hit so hard, we need to start with a mystery that is older than spaceflight itself. For more than a century, scientists have been trying to explain cosmic rays. Cosmic rays are tiny, charged particles with enormous energy. They move through space so fast that some travel close to the speed of light. They strike Earth all the time. Some come from the sun. Some seem to come from violent places much farther away. But for a long time, one huge question would not go away. What exactly accelerates them? What is the engine? What is the real machine doing the work? Scientists had good ideas. They believed shockwaves in space could do it. A shockwave is a sudden boundary where fast-moving material slams into slower material and energy builds up. You can think of it like the wave in front of a speeding boat, but in space it happens in charged gas called plasma. Plasma is gas so energized that its particles carry electric charge. The theory made sense. But a theory is not the same as watching nature do it. That was the missing piece. Now enter Jupiter. Not because Jupiter exploded, not because Jupiter suddenly changed color, but because Jupiter has something enormous around it. A giant magnetic shield. A magnetic field is the invisible force around a planet that can guide charged particles. Earth has one. Jupiter's is vastly larger and stronger. When the stream of charged particles flowing out from the sun crashes into Jupiter's magnetic field, it creates a bow shock. A bow shock is the front edge where that solar wind slams into the planet's magnetic barrier. And just ahead of that sits a chaotic zone called the foreshock. The foreshock is a messy region where particles bounce, twist, and sometimes gain huge amounts of energy. Scientists had already seen hints of this process near Earth. NASA missions like MMS and Themis showed that electrons near Earth's foreshock can become highly energized. Electrons are tiny charged pieces of atoms. That was exciting. But Earth is not Jupiter. Earth's magnetic system is much smaller. So the big question was simple. If the same process works near a much larger magnetic obstacle, will the particles come out even faster? NASA's Juno spacecraft helped answer that. And while orbiting Jupiter, Juno passed through the planet's foreshock region and measured high-speed electrons. Not just fast, faster than what had been seen near Earth. And this was the shocking part. The increase in speed matched what scientists expected if the same acceleration process scales up with the size of the shock. In plain English, the bigger the magnetic obstacle, the more powerful the particle accelerator can become. That matters because scientists have long suspected that giant shock systems around exploding stars help create cosmic rays. A supernova is the violent explosion that happens when a massive star dies. Around those explosions, shock waves race through space. For years, researchers believed those shocks might be cosmic ray factories, but they could not go there and measure the process up close. Those places are too distant and too extreme. Jupiter gave them something different, a nearby, measurable version of the same kind of physics. And that is where this stops being just a Jupiter story. Because Juno's data suggested that the relationship seen near Jupiter matched the same pattern scientists used to describe far more extreme cosmic particle acceleration. That does not mean Jupiter is secretly becoming a star. It means Jupiter may be showing us a smaller local version of a much bigger universal rule. A real working example, a live demonstration, a bridge between our solar system and deep space violence. Think about how wild that is. For decades, humanity stared into the sky trying to understand events happening light years away. And one of the clearest clues may have been hiding near a planet we can see with backyard telescopes, not because Jupiter wanted attention, but because nature often repeats itself. The same basic process can appear on different scales. A little like how a ripple in a sink and a giant ocean wave follow some of the same rules, even though the scale is completely different. That alone would make this one of the most important Jupiter stories in years. But Juno did not stop there. Because once scientists started looking carefully, Jupiter kept breaking expectations in every direction. Let's talk about the images for a moment. People hear NASA images and think the big reveal must be visual. A new storm, a glowing cloud, a weird object, something obvious. But that is not always how discovery works. Sometimes the image is the doorway, not the answer. Sometimes the photograph gets your attention, while the deeper instruments tell the real story. That is exactly what happened with Jupiter. In May 2026, Juno captured a striking close view of Thebe, one of Jupiter's inner moons. Thebe is not famous like Europa or Io. Most people have never even heard of it. But the image mattered. Juno took it from about 3,100 miles, or 5,000 kilometers, away at a resolution of about 1.9 miles, or 3 kilometers per pixel. That may sound technical, but here is why it matters. This was a close, real look at a small moon that helped shape Jupiter's faint gossamer ring through dust shed from its surface. So even a grainy black and white image becomes evidence in a bigger story. Jupiter's system is not static. Its moons, rings, radiation, and magnetic environment all interact. Everything touches everything else. And there is another twist. The instrument that captured that image was not even built as a glamour camera. It was Juno's Stellar Reference Unit, mainly designed to help the spacecraft navigate by imaging star fields. But because it works well in very low light, it became a powerful science tool too. That detail matters because it shows how exploration really works. A mission goes out with one plan. Then reality shows up and reveals new uses, new patterns, and new questions. That has happened again and again with Juno. The deeper Juno looked, the clearer it became that Jupiter is not simply big. It is disruptive. It keeps forcing scientists to update old assumptions. One of the clearest examples came when Juno helped redefine Jupiter's very size and shape. That sounds small, almost boring until you realize what it means. For decades, the planet's physical dimensions came from much older radio data collected by Pioneer and Voyager in the 1970s. Juno used newer radio occultation data from 13 flybys and included the effects of Jupiter's zonal winds. Radio occultation is a method where radio signals pass through an atmosphere, and scientists study how those signals bend and slow down. That lets them estimate conditions deep in the atmosphere. The result? Jupiter turned out to be slightly smaller and more squashed. NASA reported that Jupiter is about 5 miles, or 8 kilometers, narrower at the equator, and 15 miles, or 24 kilometers, flatter at the poles. Those are not huge changes by everyday standards, but in science, small corrections in a key reference object can ripple outward. Jupiter is used as a calibration standard for giant exoplanets. Exoplanets are planets orbiting other stars. When astronomers study distant giant worlds, part of their understanding is anchored to what we know about Jupiter. So if Jupiter's numbers shift, even slightly, that can affect how we interpret worlds far beyond our solar system. Now pause there. That means Juno was not only changing our view of Jupiter, it was quietly changing the way we measure other planets we may never visit. That is the kind of discovery people miss when they only look for flashy headlines. The strangest discoveries are often not the loudest ones. Sometimes the big shock is learning that a number printed in textbooks for decades was not quite right. And then there is Jupiter's North Pole. This is where the planet starts to feel almost unreal. Juno gathered data that helped scientists build a better model of the jet stream around Jupiter's cyclone-filled North Pole. It also gave the first temperature measurement of the North Polar stratospheric cap. That region was found to be about 11 degrees Celsius cooler than its surroundings, with winds exceeding 100 miles per hour, or 161 kilometers per hour. A colder cap wrapped in fierce winds. That is already strange. But it gets stranger. Jupiter's polar cyclones do not behave like hurricanes on Earth. On Earth, hurricanes usually form at lower latitudes and fall apart before ever reaching the poles. They need warm, moist air to keep going. Jupiter's storms are different. They crowd near the pole. They drift through a process called beta drift, which is tied to the planet's rotation and the storm's own circular motion. And when they get close, they do not simply die. They begin interacting with each other, almost like springs pushing and bouncing off one another. That image is incredible. Continent-sized storms gathered near a pole, packed into a long-term pattern that feels more like mechanical choreography than weather. If you are enjoying this so far, hit subscribe before the next discovery drops, leave a comment with the word Juno, and share this video with someone who loves science but hates boring explanations. Now let's go even deeper, because Jupiter is not only changing how we think about space weather and planetary storms, it is also exposing what is happening beneath the surface of one of the most violent moons in the solar system. That moon is Io. Io is the most volcanically active world we know. Its surface is full of eruptions, lava, and constant change. Juno used data from different instruments, including its microwave radiometer and infrared mapper, to study what lies below Io's crust. What scientists found was startling. They saw evidence of still warm magma below cooled crust across many parts of the moon. Magma is molten rock beneath the surface. According to NASA, about 10% of Io's surface may contain remnants of slowly cooling lava just below the top layer. In other words, Io is not only erupting in isolated hotspots. It may be carrying hidden heat almost everywhere. That finding matters because it helps explain how Io renews its surface so quickly. It also gives scientists clues about how heat escapes from inside a world under extreme stress. Io is constantly flexed by Jupiter's gravity and the gravity of nearby moons. That squeezing creates heat inside the moon. So once again, Jupiter is at the center of a system that acts like a natural physics lab. Not a clean one, not a simple one, but a powerful one. This is why the phrase, real images reveal a strange discovery, is more accurate than it sounds. When the images are real, the discoveries are real. But the strange part is not one single object in one single frame. The strange part is the pattern that keeps appearing. Every time Juno gives us a clearer look, Jupiter becomes less familiar, not more. The biggest planet in our solar system keeps acting like a place we barely understand. And maybe that is the deepest reason people connect with stories like this. Not just because space is beautiful, but because it is humbling. We like to think that the basic map is finished. We imagine that the major planets were figured out long ago, and now science is only polishing details. Juno keeps proving the opposite. The details are the revolution. The closer we look, the stranger the world becomes. Now let's return to the core discovery, because this is where the emotional weight of the story really lands. For over 100 years, cosmic rays were part of a puzzle with missing pieces. Scientists could detect them. They could estimate their energy. They could trace some of their likely sources. But the exact acceleration mechanism remained frustratingly difficult to confirm. Juno did not solve the entire mystery in one shot. That would be too simple. Science almost never works that way. But it did something just as important. It gave researchers direct evidence that a shock-driven acceleration process really can push electrons to extraordinary speeds in a much larger planetary environment. That matters for another reason, too. Space physics is filled with theories that look elegant on paper and then fail when nature gets involved. Reality is messy. Magnetic fields twist. Particle paths scatter. Local conditions change everything. So when a prediction survives contact with real data, especially data from a place as extreme as Jupiter, scientists pay attention. This was not just a pretty idea anymore. It was physics observed in action. Still, we should be careful. Careful does not mean less exciting. It means honest. Juno's findings strongly support the scaling relationship between larger shocks and faster particles, but that does not instantly close the case on all cosmic ray origins. There is still a huge gap between Jupiter's environment and the far more extreme environments around supernova remnants. Scientists still need to test whether the same relationship holds across all scales. They need more observations, more models, more comparisons. So the truth is not mystery solved forever. The truth is better. The universe just handed us a much stronger clue. And the clue came from a planet many people thought they already understood. That is the part I cannot get over. Jupiter has been observed since ancient times. Galileo saw its moons centuries ago. Modern missions have studied it for decades. We have paintings, simulations, textbooks, documentaries, and endless images of its clouds. Yet one spacecraft orbiting there since 2016 is still changing core ideas, still correcting measurements, still exposing unseen processes, still making experts say, in one way or another, we did not expect this. There is something powerful in that, because science is often imagined as a straight path from ignorance to certainty. But real science is closer to a conversation with reality. You ask a question, reality answers. Then you realize your question was too small, so you ask a better one. That is what Juno has forced scientists to do over and over again. Ask the first question, what is Jupiter's magnetic environment like? Answer, more powerful and more useful than expected. Better question, could it help explain cosmic particle acceleration across the universe? Ask another question, do we at least know Jupiter's size by now? Answer, not as precisely as we thought. Better question, how many other measurements depend on that reference? Ask another, are Jupiter's storms just larger versions of Earth's? Answer, no. Better question, what new rules of atmospheric behavior are we seeing there? Ask one more, is Io only violent on the surface? Answer, not likely. Better question, how much hidden magma is moving below that crust right now? The pattern is clear. Jupiter is not giving us tidy answers. It is giving us better questions. And honestly, that is where science becomes thrilling, not when everything is wrapped up, but when the universe opens a door you did not even know was there. There is also a lesson here about images themselves. We live in a time when people scroll past spectacular space photos in seconds. A planet, a moon, a storm, another post, another thumbnail. But an image from a mission like Juno is never just decoration. Behind every frame is trajectory planning, instrument design, years of engineering, and layers of scientific meaning. A close image of Thebe is not just a moon portrait, it is a clue about ring formation. A view of Jupiter's poles is not just dramatic weather, it is evidence about atmospheric dynamics on a scale Earth cannot copy. A visual record of a mission is the visible edge of a much deeper story. And that brings us back to the phrase, strange discovery. Because the strange thing is not only what Juno found, it is how many different parts of Jupiter's system seem to be connected. The rings are tied to small moons. The moons are tied to tidal heating and volcanic activity. The magnetic field shapes radiation and particle behavior. The solar wind meets that magnetic field and creates shock regions. Those shock regions may help explain cosmic rays, which connect all the way to violent stellar explosions across the galaxy. That is not one isolated discovery. That is a chain, a whole system speaking at once. If this video has already changed the way you see Jupiter, do this second signal boost. Save it for later. Send it to the friend who always says space is overrated, and subscribe so you are here when Juno's next pass gives us something even weirder. Here's the part that should stay with you. Juno is still working. The mission is not over. NASA has already extended it, and that means the spacecraft is continuing to move through some of the harshest radiation belts in the solar system. Those regions are dangerous. The environment around Jupiter is brutal, yet Juno keeps flying, measuring, and sending home data. Every pass is another chance to catch something unexpected, another chance to watch theory meet reality, another chance for Jupiter to embarrass our assumptions. So what comes next? Maybe the scaling relationship Juno revealed will keep holding as scientists compare it to other environments. Maybe it will help lock down one of the best explanations yet for how some cosmic rays gain their energy. Or maybe future observations will show that the rule breaks somewhere, and researchers will have to rethink the whole story again. That would not be failure. That would be progress. Because the goal of science is not to protect old ideas. It is to survive contact with the truth. Maybe Juno will show that Jupiter's inner moons and rings are interacting in ways we still underestimate. Maybe it will reveal new behavior in the radiation belts. Maybe Io will prove even more active than current models suggest. Maybe the polar storms will shift into a pattern nobody predicted. Every option is exciting, because every option means the solar system is still alive with unanswered questions. And that matters more than people realize. When we talk about space, we often talk as if discovery belongs to the past, as if the great era of revelation happened when the planets were first mapped and named. But that is not true. We are still in it, right now, in our lifetime. A spacecraft around Jupiter is still sending back clues that can alter physics, planetary science, and our understanding of worlds beyond our own. That is not history. That is the present tense. So the next time you see an image of Jupiter, do not just see beauty, see evidence. See a planet whose magnetic shield may be helping explain how the universe accelerates particles to enormous energies. See a world whose storms do not behave the way our instincts expect. See a giant planet whose size had to be corrected after decades. See a moon like Io with hidden heat under its crust. See a small moon like Thebe quietly helping shape a faint ring. See a system that looks calm from far away and turns wild the moment we get closer. That is what makes this story unforgettable. Not because Jupiter gave us one weird image, but because real images, real measurements, and real evidence are all telling the same deeper truth. We are still beginners out there, even with our machines, even with our equations, even with decades of exploration behind us. The universe is still capable of showing us something that feels impossible until the data comes home. And maybe the most unsettling part is this. Somewhere around Jupiter, in that storm-filled, radiation-soaked, magnetically violent environment, another discovery may already be unfolding. Another clue may already be moving through Juno's instruments. Another correction to our understanding may already exist, waiting for scientists on Earth to notice it. The signal may already be on its way. So when people say Jupiter is just a giant gas planet, remember this moment. Remember that one world in our own solar system may be helping explain particles that race across the galaxy. Remember that a moon most people ignore can shape a ring. Remember that a planet we thought we knew can still surprise us at the level of physics, weather, structure, and scale. And remember that discovery is not finished, not even close. Because Jupiter is not just sitting out there. It is teaching. It is testing. It is warning us not to confuse familiarity with understanding. And thanks to Juno, we are finally listening. One last thing before you go. If this made you feel that mix of wonder and unease that great space stories should create, like the video, subscribe for the next mission breakdown, and share this with someone who needs proof that the universe is still full of shocks we never saw coming.